Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 7th lecture of Thermodynamics 2. Lecture 7. The contents of lecture 7 are steady flow energy equation applied to throttling devices, steady flow energy equation applied to heat exchangers, numerical problems and conceptual questions and answers. Steady flow energy equation applied to throttling devices. So first we will discuss what are throttling devices. So the definition of throttling device is it is a device which restricts the flow and cause a significant pressure drop in a fluid. So it will convert a high pressurized fluid to low pressurized fluid flowing through the throttling device. So the example of throttling devices are throttling valve, capillary tube and porous plug. These are the three examples which are mentioned in your book. So the example of throttling valve, and this is a pipe, and on the left side it is a high pressure is entering through the left side and the valve is present in the middle, and it will convert high pressurized fluid to low pressurized fluid. So physically this is a shape of a throttling valve. So it's a kind of like a tap, that is a lever and valve. So you have to rotate the lever so that portion lever will move up, and the fluid you can see has a directional change. So this directional change of the fluid will depressurize the fluid. So in a porous plug, a high pressurized fluid enters from the left side, and that is a porous plug. So it contains very small pores, and a fluid is forced to pass through these pores, and the fluid will eventually be depressurized. So the pressure of the fluid will drop significantly. The third example is capillary tube. So when a fluid passes through a capillary tube, the pressure of fluid is significantly dropped down. So that is the capillary tube. You can see this type of tube at the back of your household fridge. This is frequently used as an expansion valve in a refrigeration system. When an expansion valve is mentioned in a refrigeration system, so that means it is a capillary tube. So this is a animated diagram. So you can see from left side a fluid is entering, and there is, you can see there is a directional change in the fluid. So that direction change will significantly drop the pressure. So the main point is, in throttling devices friction is involved. So the throttling device, the process is highly irreversible because the presence of friction in this process will make it highly irreversible. So certain assumption for the throttling process is, the assumptions are change in the kinetic energy and potential energy is negligible. Therefore as we know, the main steady flow energy contain a term that has kinetic energy term and potential energy component, no? So kinetic energy change delta Ke is equal to 0 and delta P is also equal to 0. There is no work done, so W is equal to 0, and no heat interaction, so the process is adiabatic. No heat enter or leaves the system, therefore the Q term will also be 0. So the assumptions are mentioned in the here as well. So we know that this is the complete form of steady flow energy equation. So the first term is heat term, second is enthalpy at the inlet, Gz1 is the potential energy component at the inlet, C1 square by 2 is the kinetic energy component at the inlet, Wt is the work done, H2 is the enthalpy component at the exit, Gz2 is the potential energy component at the exit, C2 square by 2 is the kinetic energy component at the inlet. Now we will apply all these assumptions on the steady flow energy equation. For no change in kinetic energy, therefore C1 square by 2 and C2 square by 2 will be cancelled. For no change in the potential energy, Gz1 and Gz2 component will be cancelled out. For no work done, Wt component will be cancelled out. For adiabatic process and no heat interaction, Q term will be cancelled out. So H1 and H2 terms are left. Therefore H1 is equal to H2. So the note is enthalpy of the fluid before and after the throttling is equal. As this the process of throttling is constant enthalpy process, therefore it is known as isenthalpic process. On the right hand side you can see an animation of refrigeration system. It's a part of refrigeration system. Here you will know there will be a compressor. I will just write C, and you know that there will be a condenser. So it is mentioned that a fluid that is hot is coming from, that has a high pressure, is coming from condenser. The temperature will be moderate temperature, and high pressure fluid is coming from condenser. I will write it condenser. So this is the throttling device, and in the refrigeration system you know it by the name of expansion valve. So we use capillary tube as expansion valve. So expansion valve, the function of expansion valve is to reduce the pressure of the refrigerant significantly. So high pressure and moderate temperature fluid or refrigerant is entering into the expansion valve, and low pressure, low temperature vapor is exiting out, liquid slash vapor or a mixture. So the pressure is significantly reduced in the expansion valve. So you can see that this is a kind of like a spring, and it is moving, and expansion valve is reducing the pressure of the refrigerant, and then the fluid is entered into the evaporator. We have already discussed this refrigeration cycle, vapor compression refrigeration cycle, in the previous lecture as well. The main focus is that you should know that the expansion valve work is as an throttling device. So that is the, you can read, low pressure, low temperature and saturated vapor are exiting out. So the temperature and pressure both of the refrigerant is very low at the exit of the expansion valve. So for throttling devices, So particularly we are talking about the throttling valve, or you can say that we are talking about the throttling devices as overall. So there are two cases. For case 1, we will solve it for the ideal gas. So if we use ideal gas as a substance for the throttling process, so if the ideal gas is entering into a certain pipe and a throttling valve, I will write throttling valve is installed and ideal gas is moving in the pipe. So if the throttling process is occurring on an ideal gas, so the first is steady flow energy equation, and steady flow energy equation solved for the throttling device, the equation comes out to be H1 is equal to H2. That means this is an isenthalpic process. So you know that the specific enthalpy is the function of temperature. For ideal gas, specific enthalpy is the function of temperature. So specific enthalpy can be written as CPT. H is equal to CPT. For H1 you can write as CPT1, and for H2 enthalpy at the exit you can write CPT2. So for constant specific heat, T1 is equal to T2. Therefore, for using ideal gas as a substance during a throttling process, the temperature at the inlet will be equal to the temperature at the outlet. So from Gay-Lussac principle, you know that when we increase a pressure of substance, then temperature will also increase, and when we decrease the pressure of any substance, then temperature will also decrease, because P is directly proportional to temperature. Now in the throttling process, the pressure is significantly reduced. Therefore, the temperature must also be reduced. But when we use ideal gas as a substance during the throttling device or during the throttling process, the temperature at the inlet and exit will remain same. So we can not use ideal gas as a substance during the throttling process. So therefore you know that in air is considered as ideal gas. You can use air as a ideal gas, but you cannot use air in throttling process, because the main focus is to suddenly reduce the pressure, and which consequently also reduce the temperature as well. So if air is used in the throttling process, then we cannot achieve the reduction in the pressure and reduction in the temperature. When air is used, then the temperature will remain the same. Now the case 2 is for real gas. What will happen if we use real gas in the throttling process? So the answer is, if we use real gas in the throttling process, the temperature may increase, may decrease, or may remain same. So it is written, in case of real gas, pressure is reduced and enthalpy is constant, but temperature may be fall, rise, or remain constant. So this phenomena was explained in the Joule-Thomson effect. So Joule-Thomson was an experiment scientist. He performed an experiment and find what will happen if we use a real substance in the throttling process. So upon various experimentation, he deduced that the temperature of a real substance, real gas, can be increased, decreased, or remain constant. So Joule-Thomson effect, we will briefly study what is Joule-Thomson effect. So in thermodynamics, Joule-Thomson effect describes the temperature change of a real gas or liquid when it flows through a valve. That means flows through a valve means when we used this in throttling process. Or here we are using the example of throttling valve. Therefore, you can say that when a liquid or real gas passes through a throttling valve while keeping it insulated so that no heat is exchanged with the atmosphere. So in the previous example, an ideal gas was entering, now a real gas is entering into pipe, and that is a throttling valve. So what will happen when a real gas can pass through the throttling valve? So a temperature may increase, decrease, or remain same. So that is an expression for Joule-Thomson effect, where mu is the Joule-Thomson coefficient. That is the Joule-Thomson coefficient. Partial T represent the change in the temperature, where partial P represent the change in the pressure. This H means the process is isenthalpic. Small h is written for isenthalpic process. So that was the curve that was obtained after certain experimentation. So this curve is known as inversion temperature curve, and that blue line is drawn for constant enthalpy. So we will discuss this curve in the next slide as well. Now you know that for in our case, if we are moving here, so first we will discuss the right side portion when the value of mu is less than 1. If we are decreasing pressure, for mu is less than 1, if we are reducing the pressure, the temperature is increasing. So for mu less than 0, when we are decreasing the pressure, you know that we are moving from right to left, decreasing the pressure, the temperature is increasing. Okay, you know, the slope is negative. At mu is equal to 0, pressure and temperature, when we are decreasing the pressure, the temperature will remain constant. If we are decreasing or increasing the pressure, the temperature will T is equal to 0, remain delta T is equal to 0, change in temperature is equal to 0. So we are focusing on the range when mu is greater than 0. What that means is, when we are reducing the pressure, the temperature will also reduce. So we have a direct relation between pressure and temperature. So in refrigeration, we are using the range where mu is greater than 0. So the concept of Joule-Thomson effect will be discussed in the later section or in the upcoming slide as well. So here is in this lecture we have a brief discussion about Joule-Thomson effect, and that is the Joule-Thomson coefficient. For the change in the temperature and the change in pressure, for mu is greater than 0, there is a direct relation, and for mu is less than 0, the relation between temperature and pressure is inversely proportional to each other. So for cooling, we use, when we are talking about cooling, then we use the range mu is greater than 0, and we are talking about heating, then we will be using the range mu is less than 0. The value of mu or Joule-Thomson coefficient depend upon the initial temperature and and the main is the property of substance, or in our case refrigerant. So the coefficient depend upon initial temperature and the property of substance. So it depends upon if it is different for different materials. Now we will apply steady flow energy equation to heat exchanger. So first we should know what is a heat exchanger. Heat exchanger is a device where two moving fluids, one is hot and other is cold, exchange heat energy without intermixing with each other. So that is a heat exchanger shown. In industry, these are very large heat exchanger are shown. So you will see that two fluid, one hot fluid is entering from here, hot fluid, in, and exiting here, hot fluid out, whereas cold fluid in and cold fluid out. So these are the inlet and outlet of heat exchanger. This is known as channel head. Tube bundles are shown in the yellow are these are tube bundles or tube, you can see them. These are baffle to restrict the flow or to decrease the velocity, so there is greater time for heat to exchange, baffles. So that is an industrial heat exchanger. So you see that a hot fluid is entering from the above. See that hot fluid is entering, so it is moving in a that is a U-type heat exchanger. So there are two portions, one are tubes and the other larger portion is shell. So the hot fluid is moving in the tubes, whereas cold fluid is moving in the shell. So here you can see that. So blue is the cold fluid is entering from left side, and upon exchanging the heat with the hot fluid, the temperature of the cold fluid is raised. So if we draw a temperature and time diagram, TS diagram, so hot fluid is line curve is shown in the red, and where the cold fluid curve is shown in the blue. So you can see, let's suppose the temperature at which the cold fluid enter is 20 degrees centigrade, so it will exchange heat and temperature of the cold fluid will raise. So the exit temperature will be, let's suppose it is 40 degrees centigrade, and hot fluid is entering at 90 degrees centigrade, so the temperature of the fluid will decrease, and let's suppose the hot fluid is exiting at 50 degrees centigrade. So temperature of the hot fluid is decreasing, whereas the temperature of cold fluid is increasing. We may use a combination of we may use a multiple number of heat exchanger in a row if we want to increase a temperature significantly. If we want to increase a cold fluid, so if we will pass first the inlet temperature of cold fluid will be 20 and the exit will be 40. So we will enter the 40 cold fluid into the next heat exchanger, then it will be increasing in a stepwise manner. So in numerical, usually this type of diagram is shown. So you can see that hot fluid is entering from left and cold fluid is also entering from the left. So you should know there are two types. One is known as parallel flow heat exchanger, where the flow of the fluid is is cold and hot fluid is in the same direction. Let's suppose if the hot fluid is entering from this side and exiting from this side, and cold fluid is entering from left side and hot is entering from the right side, then the flow is known as anti-parallel flow or counter flow. Usually we use the term counter flow heat exchanger and parallel flow heat exchanger. If the direction of the fluid hot and cold is same, then we say that is a parallel flow heat exchanger. If the direction of the fluid is opposite, then we say that that is a counter flow heat exchanger. So there are assumption of heat exchanger. It is a steady flow. Change in kinetic and potential energy are negligible. So the kinetic energy and potential energy component in the steady flow heat equation will be 0. Insulated, therefore no heat transfer from the surrounding, so Q term will be 0, and no external work done is, so the term will be 0. We will apply steady flow energy equation to the heat exchanger. So you must remember that the direction is same, hot and cold fluid direction is same, so we are solving the steady flow energy equation for parallel flow heat exchanger. It is also mentioned here, parallel flow arrangement. Energy at the inlet and outlet are same. That is the main form of steady flow energy equation. H1 is equal to H2. We will apply all the assumption mentioned in the previous slide. So H1 is equal to H2. Enthalpy at the inlet and exit is same. So two fluid are entering, so the HC in, so enthalpy of cold fluid that is entering plus enthalpy of hot fluid that is entering is equal to the enthalpy of cold fluid that is exiting out, and enthalpy of hot fluid that is exiting out will be equal. Left hand side will be equal to right hand side. So if we will multiply the entire equation with the mass flow rate, then m dot c, so mass flow rate of cold in is equal to mass flow rate of cold fluid that is exiting, mass flow rate of hot fluid that is entering, and mass flow rate of hot fluid that is exiting will be same. So because that is a steady flow energy, steady flow process, therefore mass flow rate. So the mass flow rate, let's suppose I will write it. Let's suppose hot fluid in, hot fluid is mass flow rate of hot m dot h. Let's suppose it is 2 kg per second, and mass flow rate of cold fluid is 5 kg per second. Then mass flow rate at out will also be 5 kg per second, and mass flow rate for hot fluid exiting is equal to 2 kg per second. That will be same. So we have multiplied the mass flow rate of respective term, hot and cold fluid, and left hand mc in minus mc out into mass flow rate c in, mass flow rate of cold, and is equal to mass flow rate of hot fluid into enthalpy of hot at the exit minus enthalpy of hot at the inlet. So that is the steady flow energy equation reduced for heat exchanger for parallel flow heat arrangement. Now we will solve a numerical for heat exchanger. The statement of the numerical is in a co-flowing. So sometime it is written as parallel flow or same direction or co-flow. So all these terms means the same, that the flow is parallel flow. Heat exchanger mass flow rate is given as 1 kg per second, and the temperature is 500 Kelvin, flowing into one channel, and 2 kg per second mass flow rate of cold fluid, air flowed in the neighboring channel at 300 Kelvin. If it is infinitely long, what is the exit temperature? So we have to find the exit temperature. Sketch the variation of T in the two flow. So right hand side we will sketch, we have to sketch the, and x is the distance or length, you can say that. What is the change with respect to length of the heat exchanger? So from continuity equation, so let's suppose that the blue one is the hot and 2 green is the cold. So you can see that green is cold and blue is the hot. So mass flow rate m dot 1 will be equal to m dot 3, m dot 2 will be equal to m dot 4 because of continuity equation. That is what is written here. Mass flow rate of hot fluid entering and exiting will be the same, and mass flow rate of cold fluid that is entering and exiting will be the same. So energy equation, we will apply the energy equation we have just derived for the heat exchanger in the previous slide. So for same enthalpy, so you know that the process is isenthalpic, we will the equation is reduced. And for constant specific heat, the C term will be cancel out, and the H term, enthalpy term, will be converted into temperature term. So when we solve for the T4 temperature, so here we have assumed one that the exiting temperature of cold and hot is same. So that is written for same temperature, exit temperature. So let's suppose the temperature of the cold fluid entering is 300 and the hot fluid entering is 500. So the exit temperature of hot and cold fluid will be the same. So the temperature of cold and hot fluid exiting is 367 Kelvin. So here is the variation of temperature of two flows is in the Tx diagram is shown. Now we will solve another numerical for heat exchanger. The statement of the problem is: consider a water-cooled condenser in a large refrigeration system in which R134A is the refrigerant fluid. So R134A is a refrigerant whose properties are mentioned at the end of your book. For certain property, you can go at the end of your book for R134A refrigerant properties. The refrigerant enters the condenser at 1 megapascal pressure and 60 degree centigrade temperature. At the rate, mass flow rate is given as 0.2 kg per second for refrigerant, and exit as a fluid, exit as a liquid at 0.95 megapascal and 35 degree centigrade temperature. Cooling water enter the condenser at 10 degree centigrade and exit at 20 degree centigrade. Determine the rate at which cooling water flows through the condenser. So we have to determine the mass flow rate of cooling water. So this is a shell and tube type heat exchanger shown, in which from left hand side water is entering in the shell, where as the refrigerant is entering into the tubes, multiple tubes. So R134A is in the vapor form and comes out in the liquid form. So there will be increase in the temperature of the water, because water is here is to cool down the refrigerant. So we will solve. So analysis with this control volume. So the dotted line shows the control volume. We have two fluid streams, the R134 and the water entering and leaving the control volume. Change in the kinetic and potential energy is negligible. Therefore, no work done and no heat transfer between the system and surrounding. So we will apply the steady flow energy equation and perform the analysis, where kinetic and potential energy terms will be neglected. Work done is 0 and heat transfer between system and surrounding is 0. Therefore, Q term will also be neglected. So that is the energy steady flow energy equation for heat exchanger. So if we use R for the subscript for refrigerant and W as a subscript for water, then the mass flow rate and enthalpies are written in this form: m dot R into HIR plus m dot W HIW is equal to m dot R enthalpy at the exit of refrigerant into m dot W enthalpy of at the exit of water. So as I have mentioned previously that R134 steam table are at the end of your book. Now we know the temperature and pressure at the inlet and exit. At the inlet temperature is 60 degrees centigrade and pressure is 1 megapascal. Where at the exit the temperature is 35 degrees centigrade and pressure is 0.95 megapascal. So corresponding to these values, we will find the enthalpy from the steam table for refrigerant R134A. So value of enthalpies are written. So mass flow rate of water will be find out. So mass flow rate of water is 0.919 kg per second. So there is another method. Second method is also shown here, that you know that the rate of heat transfer is equal to m dot Cp delta T. So H is equal to Cp delta T. So we have replaced the Cp delta T term with the enthalpies at the exit and inlet of refrigerant. So we will find the heat transfer rate for refrigerant. So here we will use the concept of conservation of energy. Heat loss by the refrigerant will be equal to the heat gain by the water, because that is an adiabatic process. Therefore no heat will be lost to the atmosphere or the surrounding. So all the heat lost by the refrigerant will be equal to the heat gain by the water. So the heat transfer rate will be same. Therefore mass flow rate of water can be find out. That is the second method, and in the previous slide we have discussed the first method. You can solve the numerical with the help of both methods. So third numerical of heat exchanger. A two fluid heat exchanger has 2 kg per second liquid ammonia. So in the steam table you will also find the table for liquid ammonia as well. So mass flow rate is 2 kg per second and the temperature is 20 degrees centigrade and pressure is 1003 kilopascal. So inlet and exit in this type of numerical are mentioned with state 1, 2, 3 and 4. So entering the state 3 and exiting at the state 4, it is heated by a flow of 1 kg per second nitrogen at 1500 Kelvin state 1, leaving at 600 Kelvin state 2. So high temperature nitrogen is entering from state 1 and exiting from state 2. So the temperature of nitrogen is reduced, whereas the temperature of ammonia is increased. Find the total rate of heat transfer inside the heat exchanger. Sketch the temperature versus distance for the ammonia and find the state 4 temperature and specific volume of ammonia. So we don't know the exit temperature of ammonia. So as the temperature of nitrogen is dropping, therefore the temperature of ammonia will be increasing. So using continuity equation, so the mass flow rate of nitrogen and mass flow rate of ammonia at the inlet and exit will be same from continuity equation. So we will find the enthalpies from table 8.8 A.8. So against the temperature and pressure values you will find the enthalpy values. So H1 and 2, these are the enthalpies of nitrogen. So you will find these values at the end of your book. So against the temperature values you will find the values of enthalpies. So you will find the heat transfer rate, that is mass flow rate of nitrogen, into enthalpy at the exit minus enthalpy at the exit of nitrogen. Enthalpy values are found at the end of your book. So when you insert the values you will find the heat transfer rate of nitrogen. So now you when you use the value of Cp that is mentioned in table A.5 for nitrogen, so heat transfer rate out is less than the heat transfer rate found in the enthalpy. So when you put the value of Cp of nitrogen and temperatures of nitrogen at the inlet and exit, the heat transfer is 937.8 kilowatt, whereas when you have found the heat transfer rate from the values of enthalpies, that comes out to be 1053.5 kilowatt. So for stage 3 and 4, the enthalpy will also remain constant. H4 is equal to H3 plus m dot H1 minus H2 divided by m dot 3. So H4 comes out to be 274.3 is the value of enthalpy at state 3. 1053.5 is the total mass flow rate into change in the enthalpy at state 1 to 2. So H4 is the enthalpy at state 4. So it is 801.4 kilojoule per kg. So the value of enthalpy that comes out at state 4 is less than the saturated vapor state enthalpy mentioned in the table, which shows that this is a two-phase process. So I will write it here. So when we were discussing about the pure substance chapter, that is a dome curve. So temperature at the saturated vapor line is Hg. So if the enthalpy is less than the saturated vapor enthalpy, then the substance is in vapor and liquid. The under the dome region is vapor plus liquid. So that means two-phase mean vapor plus liquid, because the enthalpy is less than the Hg. So in this step we will find the dryness fraction at the state 4. So what is dryness fraction? It is the mass of vapor divided by total mass. So sometimes it is written as quality or dryness fraction. So X4 comes out to be 0.43147. That means it contains 43.147% of vapors, where other is approximately 57% is liquid phase. So in the next step V4 we will calculate the specific volume at the state 4. That comes out to be 0.05623 meter cube per kg. So the temperature is 25 degrees centigrade. This is the boiling temperature for 1003 kilopascal. So this means that is the saturation temperature. T sat for P sat is equal to 1003 kilopascal. So when we were discussing about the pure substance chapter, so we know that the T saturation depend upon the P saturation pressure. So that is the temperature and distance curve is shown. So for ammonia, the temperature will increase from 293 to 298 and then remain constant because that is a phase change process from 3A to 4. So conceptual questions: how does a nozzle or spray head generate kinetic energy? By accelerating the fluid from high pressure toward the low pressure, which is outside the nozzle, the higher pressure pushes harder than the lower pressure. So there is a net force on any mass element to accelerate it. So the spray head is a type when like you use deodorant. So when you push that down, so the high pressure fluid is exiting out. So the fluid is accelerating from high pressure toward the low pressure. So the pressure at the inlet of the can is high and atmospheric pressure is low. So the higher pressure pushes harder than the lower pressure. So the fluid is exiting the nozzle with a very high pressure. So the pressure after the fluid after passing through the nozzle is low fluid pressure. Therefore, the mass element is accelerated through the nozzle. So what is the difference between nozzle flow and throttle process? In both process, a flow moves from higher to lower pressure. So in the previous lecture we have discussed about the nozzle. So that is a nozzle. Velocity is increased and pressure is decreased. Whereas in throttling process, let's suppose that is a valve. Pressure at the exit is very low with respect to pressure at the inlet. So in both cases, the pressure is reduced. In nozzle, the pressure drop generate kinetic energy, whereas that does not take place in the throttle process. The pressure drop in the throttle process is due to the flow restriction and represent a loss. So you know that throttle process is highly irreversible. So there is the flow, the direction of flow, you see that is changed in the valve. So the mechanism of valve is such that the direction of the fluid is changed. So restriction is caused and this is a irreversible and this restriction cause a friction. So throttle process contains friction and highly irreversible. So pressure is reduced in both process, but friction is present in the throttling process, therefore it is reversible. Next conceptual question is, if you throttle a saturated liquid, what happens to the fluid state? What if this is done to the ideal gas? The throttle process is approximated as a constant enthalpy process. You know that the throttling process is enthalpic process. Changing the state from saturated liquid to lower pressure with the same H gives a two-phase state. So some of the liquid will vaporize and it become colder. So throttling valve is mentioned here. So H minus, that is a constant temperature line, are shown in the black. I will turn it to the pointer option. So you can see that that's the dome portion. PV graph is written, is shown, and that is a dome portion, and that is a constant temperature line. In PV in PV graph, the temperature line or a constant temperature line or have a downward trend. So if we are here and there is sudden drop in the pressure, so if we are in the superheated region, then we will move to the saturated. If we are in the vapor and liquid under the dome, which contain vapor and liquid both, we will move to the saturated liquid line. So that is mean here is shown that changing state from saturated liquid to lower pressure with the same age. So for ideal gas, a lower pressure with the same edge gives a two-phase state, that is the two-phase state, liquid and vapor. Now if the same process happens in an ideal gas, then same H gives the same temperature, because H is the function of temperature at lower pressure. So we know that for ideal gas, specific enthalpy is the function of temperature only. Air at 500 kilopascal is expanded to 100 kilopascal in a two steady flow cases. So the pressure is reduced and volume is increased. So one case is nozzle and the other is turbine. The exit state is the same for both cases. What can you say about the specific turbine work relative to the specific kinetic energy in the exit flow of the nozzle? So we have to find what is the relation between the specific work in the turbine done and the specific kinetic energy, that is of the fluid exiting out of the nozzle. For these single flow devices, let us assume that they are adiabatic, so no heat is transferring to the surrounding. So turbine does not have any exit kinetic energy, then the energy equation becomes, so if the fluid exiting from the turbine does not have any kinetic energy, for nozzle the steady flow energy equation is shown, and the turbine is the second one is for the turbine. So after comparison, the nozzle delivers kinetic energy of the same amount as the turbine delivers to the shaft work. So when we compare or minus both equation, let's suppose the we minus the nozzle equation from the turbine. So Wt is equal to C2 square by 2. C2 is the kinetic energy at the exit of the nozzle. Wt is the work done by specific work done by the turbine. So this that right term side is the specific kinetic energy of the nozzle, and left is the specific work done by the turbine. So that will be equal. Lecture 7 home assignment. So you are advised to go through example problems of the topic discussed during the lecture. You should submit handwritten lecture summary report. Email it to my email address aslan@cietwa.edu.pk, and you should go through the online lecture video lecture properly. So there will be oral viva question answer in the online session. Okay, thank you very much. Allah Hafiz.